This next portion is going to be introducing a lot of concepts and a lot of units for the equations. So in order to immediately throw them out to you, I want to first go over the concept behind them. This is going to be taking a look at the sources of light. And we're going to compare the sun and the moon. So here's the sun, and we're going to draw the moon the same size, even though, of course, it is not the same size. And the sun produces light, and the moon also is bright at night as well, for different reasons, though. The sun is the body that emits the light. The moon, of course, does not produce its own light. It's merely reflecting the light that's coming from the sun. So this is reflected light. And then that light comes to our eyes here on the earth. So since this emits the light, there's a special name for the source of the light, and this is called the luminous body. Okay, luminous meaning light. And this is the reflected light, so this is going to be the illuminated body. Okay, this is what is becoming lit up because of the sun. This is the source. This is the luminous body producing the light. This is being illuminated by the light. Okay, so because this is the luminous body, this is the illuminated body, there are two terms that we're going to be using that are very close to this. And we have the luminous. Okay, for this we're using the whole luminous. This is called the luminous flux. And this is close to illuminated, and this is called the illuminance. So if you remember flux, flux is actually another word that means flow. If you remember, this term was introduced when we watched the movie on charges, when we have positive charges and negative charges inside the electrical fields and how strong that the force is in between those. And if you can imagine, like a magnet as well is constantly having this flow of a magnetic field. A charge is constantly exerting this flow of an electric field. Okay, so here we have this light source that is producing this flow of photons. So this luminous flux is the output of light. Okay, and the luminous flux is measured with the capital letter P. I don't know how it got that letter. The illuminance, on the other hand, this is measuring the amount of light that is received on the moon. Okay, so it's the measure of light. Measure of the light that's received. This measure of the light that's received, this is the illuminance. The illuminance is the symbol capital letter E. Okay, so imagine you have a light bulb and it's sitting in your room. Okay, it's a 100-watt light bulb. Okay, that's just like the sun. It's just sitting there. That light bulb is constantly emitting the same amount of light. It's the output of light. However, depending upon the distance, you could be standing very, very close to the light, and you can measure a very high amount of light because you're close to it. But the farther you get away from it, the amount of light, the measure of light, is going to decrease. So this luminous flux, this is the output, this is the source, this is the amount of light that's being put out, and the illuminance is therefore going to be dependent on distance. How much light is being reflected or received based upon the distance that it is. Here's the master formula for this, and it's going to be illuminance. The amount of light that is received is going to be proportional to the luminous flux. So the brighter that your light is, the more that you're going to be receiving. Imagine you have a 60 watt light bulb. Our luminous flux has now decreased. Well, how much will be received? Well, less light, because 100 watts is producing much more light than a 60 watt light bulb. If you decrease the flux, you're going to decrease the amount that is going to be received. Now, this is also going to be divided by the distance. And it's not just the distance, but it's going to be the distance squared. And this is going to look very familiar. It's going to be 4 times pi times the distance squared, which is very close to 4 pi r squared, which, if you remember 4 pi r squared, this is also the formula for surface area. And we'll get back to this surface area. So this luminous flux, the output of light, this is measured in lumens. So we have lumens, lumens of light. Oh, just lost the light. Lumens has the units of LM. Now this is not 1 meter, this is actually a lowercase l, LM. And the illuminance is going to be measured in lux. And lux is going to be measured as Lx. That's not 1x. So let me get a little a sheet for you. I want to show you this right here. It's a comparison of 2 different light bulbs. So this one is an incandescent light bulb. It's the older form of light bulbs where you have this filament in between 2 pieces of metal, and the electrons will flow through the filament. It'll have resistance, and then what's going to happen is the energy of those electrons will be released as light. So light's going to be emitted out from this incandescent filament that's happening on the inside of the light bulb. This is a 40 watt incandescent light bulb. You have another choice of actually getting this over here, and this is going to be a 40 watt equivalent light bulb. These are the ones that you kind of plug into little chandeliers. Okay? This one, though, is an LED light bulb. This one, it's a 40 watt equivalent, but it actually uses only 7 watts. LEDs are much more efficient because what happens with incandescent light bulbs is a lot of the energy, a lot of the 40 watts is produced as light, but a lot of that energy actually is released as heat. So this is actually using 7 watts, and it's producing more light, and it's producing less heat. So first of all, LEDs are much more efficient because they're not going to be wasting energy as heat. It's going to be putting all of its energy into light. So LED lights are actually cooler. If you were to touch this, right, when you turn the lights off, it would be very, very hot. You'll burn your finger. If you touch this, it'll be warm. So these both are producing 360 lumens. It's the output of light. This is the important thing when you're going to the store. How many lumens of light, and you'll see this on the packages, how many lumens of light are you receiving? Well, we're receiving the same lumens of light. This is the 40 watt equivalent. But take a look at this price. This price is about $10. This is $4. This is almost 3 times as much. However, look at the amount of energy consumption. 7 watts versus 40 watts. It's about 3 times more, but it uses, how much less? It uses about 6 times less energy. So actually, in the long run, this is going to save you more money by buying the LED because it's using less electricity. It's using a lot less electricity, and it's also these lifespan of this is about 1 to 2 years. These are about anywhere between 5 to 15 years. So these LED lights really, they cost a lot more, but they're much more efficient than your incandescent ones. So I just want to introduce lumens. This is the amount of light that's being produced from both of them. Okay, and again, the luminance is based upon your distance. So let's take a look at this distance factor. So imagine this is your light source here. So we're looking at distance. And here's your light bulb. Okay, and this light is being produced in 360 degrees on this flat plane, but also, if you can imagine, this being like a sphere going out. Okay, so try to draw a circle around here, and this is going out in this sphere. So here's our light source right here, and this is, we're going to say this is at 0 meters. So at 0 meters, this is our light source. Whether it be a 60 watt or a 100 watt light bulb. Okay, now imagine over here at 1 meter, okay, we have this little small square card. What's going to happen is that these photons of light are going to hit this card right here. Imagine it's also not flat like this, but it's actually facing at an angle that it's sort of upright like this. We also have some photons of light that are going to be going like that, and it will hit this. Okay? And what's going to happen is the light will then, that are in these photons of light will continue to span out, these will continue to span out, but this is going to create a shadow. So imagine at 1 meter, we're just going to say that it's full intensity, even though it's actually full intensity here. Just for the purposes of this, at 1 meter, let's just say that it's full intensity. And we're going to watch what happens now as we cast this shadow. So imagine this shadow that's being cast like this. Okay, we have a light source, we have a square card, and again, it's going to be a shadow that's going to be cast. Now let's take a look at what happens at about 2 meters. So at 2 meters, we have this now shadow that is going to be the equivalent of 4 of these squares. Okay, so now what I want you to now do is imagine we're removing now this, it no longer exists. So all of the photons that were hitting this one square right here, coming from these angles, are now hitting this square. Let's say we had 100 photons of light that were hitting this one square. That means all 100 photons are hitting this square. Well, how many photons are going to hit each square? Okay, let's say we have 100 photons of light hitting here. How many are going to fit in each square? We now have 25 and 25 and 25 and 25. So what's the intensity at 2 meters? Here we have the full intensity. Here we have 25 over 100 would give us 1/4 the intensity. Let's continue this on by increasing the distance to 3 meters. At 3 meters, we have, again, if we had the card here, it would create a shadow that looks like this. So if we had 100 photons here, 100 divided by 9, we would have about 11 photons in each of these boxes. So the intensity of the light in each box is 1/9 of what it is right here. So we have 1/9 the intensity. So remember, this illuminance is based upon the amount of light that's being produced, but also your distance, not just the distance squared, but it's 4 pi distance squared. This is sort of like the radius right here. Imagine this is your center of this sphere, and we have this, this ball that's going out. And now we have this little square now on the inside. It's on the inside of this sphere, receiving the photons of light at 1 meter. So this would be at full intensity. But when we expand this ring, this sphere that now goes out to this 2 meter range, okay, we now have, I'm trying to draw it in the curvature, we now have these 4 squares that are on the inside here. This is a measurement of the surface area on the inside of the sphere. This is the surface area of a sphere. So if the radius is 1 meter compared to 2 meters, if it's 1 meter, your illuminance is going to be it's going to be full intensity. But if it's at 2 meters, this becomes 4 pi r squared, and at 2 meters, it becomes 1 over 2 squared, which is 1/4. At 3 meters, it becomes 1 over 3 squared, which is 1/9. So we're taking a look at the intensity, and this is again related to the inverse square law. Why does light, why does magnetism, why does electricity, why does gravity, why does it all decrease as a factor of distance squared? It's because these forces are affecting a 3-dimensional universe, and in a sphere, if you were to measure the force, the magnetism, the electricity, or the light at the distance at that point away from the object, what's going to happen is it's going to be affecting it in a 3-dimensional way, but it's going to be the surface area, which is going to be the area. So that's why this formula is 4 pi r squared, and that's why all these other factors are decreasing by a factor of distance squared as well. So let's get to an actual problem. Okay, so taking a look at the formula again, we have the illuminance is equal to the flux, and it's over the surface area. So flux is measured in lumens. It's the light source. It's the amount of light that's being produced. That's not 1 meter, that's lumens. Area is measured in meters squared. Now that's not going to cancel because that's not a meter. It's lumens over meters squared. Lumens over meters squared, again, are going to be units of lux, which is going to be Lx, not 1x. So again, the illuminance is measured in lux. The luminous flux is going to be measured in lumens. So there's a lot right there that's hard. So again, here, this is the flux. This is the luminous flux. This is the illuminance at a distance. This is the source. This is what's being received. Again, the illuminance is measured in lux, and the flux is measured in lumens. So here's the problem. We have the luminous flux of a 100-watt light bulb is going to be equal to 750 lumens. Okay, we previously saw that a 40-watt light bulb is about 360, so that seems to be about right. Question is, what is the illuminance at 1 meters and 2 meters? So the illuminance at 1 meter will equal to the flux divided by 4 pi d squared. Okay, the illuminance for the 2 meters will have the same formula. So what we have here is for the flux, we have the 1750 lumens divided by 4 pi, and we're at 1 meter squared. And again, lumens per meter squared, that's going to give us the units of lux. And if you divide this on a calculator, you'll find that it's going to be 139 lux. If we go out to 2 meters, we have the same flux, it's the same source, it's the same amount of light that's being put out, divided by 4 pi 2 meters squared. And this will give you, in significant digits, it'll give you 35 lux. If you multiply this by 4, you'll get to 140. We've lost some details in using significant digits. But this is again showing that when you increase the distance by a factor of 2, you're going to decrease the illuminance, not the energy. You're going to decrease the illuminance by a factor of 4. It'll be 1/4. So this is 1/4 of the original up here. So there's a lot in this concept. We have the repeat of the inverse square law, and that's because we live in a three-dimensional universe, and you're experiencing your force at a certain distance, and you're experiencing that along the surface area of this expanding sphere. And so it's often using the 4 pi r squared because of that surface area.